Okay.
So you can start. So you may understand what I'm starting, maybe in the same way or a different way.
So will the charge density plus sigma be for the entire sphere or for only the part without the others?
Oh, no, it's for the entire sphere. Otherwise, it get cancelled, right? It's a conducting sphere, right? They can't stay separate.
So it will be only for the entire sphere.
Yeah, it's for the entire sphere. Even for a conductor, whatever they write as charge and all, it means not only at that point, it is the distributed charge over the entire sphere. Okay.
B is like outside A doesn't mean B has minus sigma and plus sigma, right?
No, B only have minus sigma.
Okay.
The other spheres are not connected. Okay.
Yes, sir.
Yeah.
Does this have something to do with equipotential surface?
Nothing specifically with that. Without, you can do directly. Nothing specifically to do with equipotential surface. I know we didn't discuss equipotential surface.
No, but like, is this that kind? Is this one of is this an example?
That you have a charge at the center and you draw the spheres, right?
Yes, sir.
Yeah, but these three different spheres are separately charged. Okay.
Okay. Over there, it's the same charge, right? Charge density.
Charge is at the center only. There's no charges on the spheres on the equipotential surface. What you see?
Okay, yeah. Okay, got it.
Charge at the center, and we are imagining concentric spheres imaginary around the sphere. Okay. Around
Okay.
So I'm not waiting. I'll slowly start. You can check whether you got the idea, same what we are trying to do or not. A, B, C are the radius. A is less, B less C. Okay. Sigma minus sigma plus sigma. You want expression for potential on each sphere. So if I take the inner sphere A, so how many contributions of potential to the inner sphere?
So 3.
3. 1. Due to the sphere A itself.
Yes, so then 1 due to B and 1 due to C.
Okay. So if I draw a small sphere only A here, it's only A. Okay. This is the radius that is given as A. The charge density is given as plus sigma. So what will be the potential on that sphere due to that sphere itself? You have two options. You can use KQ by R or you can use the sigma, anyone. This is one of the 3 cases we discussed.
So sigma by epsilon A, like small a.
Sigma A
By,
by
by, eps-
epsilon.
by
This is like sigma R by epsilon, right? R is A.
yes, sir.
Plus, now this point have contribution from sphere B, right?
Yes, sir.
For sphere B, this point is inside point on the surface of B or outside B?
So inside.
Inside. So any point inside, a sphere will produce a potential same as its on surface.
So
Will be
can you repeat?
epsilon.
I didn't hear Joanna once more.
So can you repeat it again? I didn't get the.
Yeah. I'll tell you. If this is a sphere, okay, what's the potential inside the sphere?
Same as out of the surface.
On the surface, right?
Yes, sir.
So imagine this is sphere B, okay? What's the radius of sphere B?
Small b.
Small b. The charge density is minus sigma, right?
Yes, sir.
What will be its own potential on the surface?
Sigma epsilon. Sigma by epsilon small b. Sorry,
Yeah.
minus sigma by epsilon small.
That's fine, understood. That will be same as this point also, right?
Yes, sir.
That is a point where what you're taking A, fine? The sphere.
Okay, yeah, got it. Yes, sir.
It will be minus sigma B by epsilon. I'm not sure. Any questions? This is what I told you in the beginning. If the terms, what I'm telling, if you're not clear, you get confused on the way.
So, basically the potential on B will also affect A.
Yeah, because we know a sphere has potential outside on the surface, inside also, right?
Yes, sir.
Electric field was not affecting because electric field was zero inside. Okay.
Yes, sir.
Yeah. Now, if I take a big sphere C, what will be the potential on the surface of the big sphere?
Sigma C by epsilon.
Yeah. What will be the potential of that sphere at this point? Again, A, same point.
Sigma C by epsilon.
Yeah, because it is same as that on the
Surface.
I don't know all of you are clear with this.
So I have one doubt.
Yeah.
So even though there's like a circle with, sphere with charge, for example, if we take only C and B, now B has a charge, but the point is inside. So won't the potential be same as C, no matter what charge is inside?
Once more,
Like,
can you tell me? I didn't listen to you
so
completely.
we have to take, okay, for example, B is inside C, like only B is inside C. B has whatever, like, for example, sigma density only,
Yeah.
okay, minus sigma density. But if we're taking potential on B, won't it be the same as potential on C because it's inside C? Like, won't it like be the same?
Yeah, that is only due to C, right? But B have its own charge, right?
But it's inside, yeah. So won't it like how will it
Inside,
happen?
inside is due to that sphere only we say what constant of that surface, right?
Yes, sir.
So at this point, potential is same as this surface due to that particular sphere only. If you have another sphere around that, that also have inside potential, right?
So then I have another doubt. So if you're having a sphere inside another sphere,
Yeah.
won't the potential on that sphere go to the edge, like go to C? Like if B has minus sigma, won't it go to C? Because it has to
These
spread.
are the two spheres we speak. Okay.
So
This is radius R1. This is radius R2. This is just charge Q1. This is just charge Q2. Okay.
yes, sir.
Now this potential will be contribution of two potentials. Fine.
Yes, sir.
One due to the sphere with radius r1.
Yes, sir.
One due to the sphere with radius r2.
Yes, sir.
So it will be the total of potentials of what?
Okay, of R1 and R2.
Yeah.
So what I'm asking is, like, it's a sphere inside a sphere. So
Hmm.
won't the charge on the second sphere like distribute and go to the first sphere edge?
It's not connected, right? They're not connected spheres.
Oh, it's hollow. I mean, each is
Yeah.
hollow.
The lines are just drawn to show the radius, okay?
Oh, okay. Got it.
It's not
So
a,
they're not connected. So the since they're not connected, the charge will like be in the border of that
yeah,
only.
wherever you give, it will stay there as per that.
Yes, I understood.
No, I was not connecting with respect to that, the connections, like I was only telling with respect to this. That's why I didn't get connected what you're thinking that way. Okay.
Yes, like I was just thinking like if there's a charge inside, won't it like go to the edge?
If you connect two spheres, metallic spheres, all the charges of the inner one will go to the outer one. No doubt in that. Okay.
Okay. So it shouldn't, if it's not connected, then it'll be independent.
They can't move, right? They just stay wherever you're given on that scale.
Okay, so got it.
So if all the charges go to the outer sphere, then only that one has potential.
Yeah, if all are connected, okay.
Yeah, if they're connected, so B and A won't have any
No
potential.
use of B and C then. A and B then. If you connect all of them by metals.
Okay.
I'm not
So now
sure.
I have another doubt.
Yeah.
So potential for B, won't it be potential on B plus C?
Potential on B will be potential on B due to B.
Yes, sir. And B due to C.
B due to C and B due to A, treating B as outside point of A.
Yes, sir. But then if we take, so we don't substitute that potential value into A. We just take an independent value. Like,
Yeah, we are taking three at different places and adding finally.
okay, so fine. Got it.
A, B, C are taken as three different points charges like spheres. Then we find for each one and add the contributions.
So for example, if we're like over here in the second term, yeah, you substituted for like potential on A due to B. So that will be different from potential on B due to B and C. Wait, I'll like tell the question
No,
again.
I
Like
just
I'm
want to
still
clear
have to
it.
see.
That's why I'm waiting. Okay, I'm not
Yes,
clear.
sir, yes, sir. See, so you said for potential on A, so first we got potential on A due to A. So you wrote
Yeah.
that.
Yeah, this one.
Then second, you wanted potential due to B.
Potential
So now
on that
potential,
point itself due to B. Same point.
okay, so that will be different from when we're calculating potential on B due to like everything else. We don't just substitute.
For B, right?
Yes, sir.
For B, the contribution of A will be different.
Oh, so each point the contribution is different. So we like they're not interconnected.
Yeah, 1 minute if you wait, I'll just complete. At point B, can you see this point B, right?
Yes, sir.
This point contribution of B won't change because it's on the surface.
Oh, okay, sir.
Contribution of C also won't change because it's inside C.
Okay.
But contribution of A will change because the point becomes outside now, A.
Oh, okay.
You remember potential on the surface and inside are same throughout.
Yes, sir.
Now I try writing, you can check that potential on B. Now what's the contribution of potential on B due to the inner sphere? This inner sphere, the radius is A, the point is here, which is a distance B. How you find for point outside the sphere?
It will be same as potential on B due to B.
No, I want a value because of these formulas. How you're going to apply that? Sigma
Sigma B by epsilon.
outside point. What's the formula? Outside point is not that formula, right?
Oh, sorry. Sigma by epsilon, A square by B.
Yeah. This is what I told you when I started in the beginning. If the terms are not clear, we get confused in the step.
So isn't A a point inside the sphere B? Like, shouldn't we?
Okay.
I'm confused now.
Yeah, that's what I told. Can you wait and just speak to me and go like 1 minute? Okay.
Okay, yeah, yes, sir.
Yeah. You know which contribution this? This is contribution on B due to A.
Yes, sir.
So this point is outside the sphere A or inside the sphere A or on the surface of A.
It's outside the sphere A.
Okay, tell me what's the formula for outside potential?
Sigma by epsilon A square by B.
Sigma by epsilon R square by R, right?
By X, yeah.
This is the radius of the sphere we are counting. Which sphere is producing the potential? Its radius. And this is a distance from center of the sphere to the point if you're outside.
Like, what if we consider the sphere B? Then shouldn't the point A lie inside? Can we not take it like that?
Why are you taking point A now? Point A finished already here.
Okay, so when you find the potential at B with respect to A, we should take the point B outside the sphere A, basically.
It is outside. No, we are not taking like that. Check this point. Can you see the point here?
Okay, yeah, I got it, sir. Yeah, I got it now.
I think I should go back and explain once more the potential inside, outside, and on the surface.
I think I'm fine. So when you explain C, I think it'll be fine. Yeah, I almost got it. I just listen to you.
Yeah, I'll just confirm once more. This capital R is the radius of the sphere. You're finding who is producing the potential. Okay. And small r is the distance from center of that sphere to the point where you find the potential if the point is outside.
Yes, sir. Got it.
But sir, don't we have to do it with respect to the B sphere?
All the three have to do.
So VB should be taken as a charge on B surface, right?
Yeah, B will be at its own surface itself, like this one. Pallavi.
Yes, sir.
So this won't change then. This will remain the same.
No, I'm talking about VB.
Yeah.
VB should be sigma B minus sigma B by epsilon, right?
That is potential on B due to B itself, right?
Yes, sir.
How many potentials on B? B will
Outside, on, and in.
I'm not speaking about potential of B. I'm speaking potential on B due to others.
Okay.
Potential on B will have B due to B itself, potential on
Yes,
B
sir.
itself due to A, potential on B itself due to C. Same point with respect to the sphere is different.
So I think it'll be better if we think of it as a point instead of like on the sphere. So if we take just as a point, then it's easy to like understand.
Then we should go to KQ by R, then direct formula.
And for me, like when I thought of it as a point, then I understood the concept.
I went, this is the easiest way, but this is understanding demanded more. Can I clear this off and start the other way?
Yes. So once
So can you show this way first?
Yeah, I can complete this and go. It's fine.
Yes, sir.
But can
Yes,
you complete this? I'm confused with what Pallavi is thinking now.
No, because so I thought it's only VBB. I didn't consider VBA and VBC.
Yeah, every sphere has potential contributions inside, outside, on the surface, right?
Okay, sir.
So this B will have how many contributions? This point.
3.
Yeah, contribution of A, which is taken as an outside point, right?
Yes, sir.
And contribution of B itself as surface point.
And C from outside again.
C inside point. For C, it's inside point.
Oh, okay.
B, all are with respect to this point. Okay. A will produce potential here. B will produce potential here. C will produce potential here. That point.
Yes, sir. Okay, understood.
Now, Point B, yeah, yes.
So when we say potential on B due to A, we're talking about how you have to say B as a point with respect to A. So it'll be outside of A.
Yeah, that's it.
Okay. So like we can't take it the other way around. Like
Which B?
A as a point that lies inside B.
Which point?
If you're taking VBA, instead of saying that B is a point outside A, we cannot take it as A as a point inside the sphere B.
Yeah, you can take, but that is when you calculate the potential of A, right?
Okay, yeah, I got it now. Yeah.
That we have done already. We have taken that point with respect to all the three spheres.
Yes, sir. Okay.
What I understood now, you're confusing between, you're taking one sphere and finding inside, outside, and on the surface. That's not what we are doing.
Yes, sir. Yeah. Okay.
We are finding potential of each point due to all the three spheres. For some spheres that will be inside, for some spheres will be outside, for some spheres that will be on the surface. Can I complete this one?
Yes, sir.
Okay, can you just listen 1 minute? This is a point I'm considering now. Can you see this round black?
Yes, sir. Yes, sir.
Is it inside A?
No, sir. Oh, yes, sir. Yes, sir. No.
Is it inside A?
No, sir. No, sir.
So that we should take outside contribution of A, right?
Yes, sir.
See, if you are not clear, I don't mind. I'm staying here slowly. You should confirm yes, yes, no, no, no issues in that. Okay? No,
So that point is affecting A. That's what you mean to say, right?
no. This point is affected. Yeah, point is affected by A, affected by B, affected by C.
So how is it affected by A?
Because A will have potential outside. If this is a sphere A, fine.
Yes, sir.
Do it have potential here?
Yes, sir. Okay.
So this point is a B point. Fine, check like that. See.
Okay. Yes, sir. Yes, sir.
So this point have influence of A sphere. This point have influence of B sphere. This have influence of what? C sphere.
So if we're going to find for C, it will be on the surface of C. There'll be VCC.
Yeah.
Then VBC will be outside of B, and then VCA would be outside of A.
I want to listen once more because I'm not that greatly connected with what you say.
Okay, it'll be
Slowly.
for
Slowly, okay.
yeah. Okay, for C, it'll be on the surface.
Okay, you're telling about third point C or
C, yeah, third point.
say I'm only B. Okay, fine. Third point C. Yeah.
Yeah, so on that, due to C itself, it'll
Yeah.
be on the surface formula.
Yes. Yes.
Due to B, it'll be a point outside potential.
Definitely, because that point is outside B sphere, right?
Yeah, and due to A also, it'll be a point outside
Outside the
C.
sphere. Yeah, correct. I think you got the point now. You're taking one point common and counting the effect of other three spheres.
Yes, sir. Okay.
So could I just explain once? I think I got it. Like, could you tell me if it's right?
Yeah.
So first, if we take for A, the point we're taking is just a point.
I clear everything once more. I think that's better. So many diagrams are here.
Yes, sir. Yes, sir.
And our aim is to understand, not to by heart, okay? I don't know you got what I said. I don't want to get the answer just.
Yes, sir.
I'm just reviewing the formula once more. Maitri, you can do that instead of me.
Oh, yes, sir. Okay, so first, we'll find total potential on A.
No, I'm leaving this sphere. I'm just taking one single sphere. Okay.
Okay, fine. So, for potential of point outside, you'll get sigma by epsilon r square, radius
Which R?
square by,
Just I'm confused. There is my
yes,
confusion.
sir.
Which are you?
Radius square by distance.
Radius of the sphere you count, right?
Yes, sir. Radius of sphere, the whole square by the distance.
So if this is my sphere, I'm finding the potential. That should be R square.
Yes, sir.
Then what should be the denominator R?
The distance, so that's like if you name it like small r, x, yeah, so it'll be x.
If you take the distance from center to that point, that will be the distance here.
Yes, sir.
So these three, or this is the contribution of the sphere, and this is a distance from center of that sphere to the point. Fine.
Yes, sir.
Okay. Then what on the surface now?
So for on the surface, it'll be sigma by epsilon into radius of the sphere.
Yeah. Which sphere effect
Capital
you're
R.
counting? That one. Okay. Fine. Inside.
So inside, since the charge inside will be zero as all distributed on the surface, it'll be same as sigma by epsilon radius.
Yeah, I just want the formula part one. That concept is clear to me. What you told.
Sigma by epsilon radius.
Okay. Now, which point you're taking first?
So we'll take A.
A. So I'm just drawing the sphere A. Okay.
So can we just name the point like X, Y, Z so it'll be easier instead of getting confused?
So there are points here A, B, C. Can you see this?
So but isn't that the name of the sphere?
Okay. Then why don't we take same points instead of X
Okay.
again? Okay.
Okay, sir.
Yeah.
So potential on point A.
So this is sphere which one?
Yes, sir.
This is the A sphere. Okay.
Yes, sir.
Okay. This is a point what is marked as A.
Yes, sir.
It have three contributions, right?
Yes, sir.
Yeah, repeat. You can start now.
Okay, so first we'll have to find the total potential on A. So for that we have three contributions. The first one is potential on A due to A.
This one, right?
So
This
potential of A due to A is because we have to take the surface formula because the point is on the surface of the sphere. So you will get sigma by epsilon into small a.
Anyone have a confusion? I use this formula. Joanna?
No, sir, understood.
Okay, fine. Now I'm finding the effect at A due to another sphere. Maitri, you want to tell me what you're finding because of what? Okay.
Yes, sir.
Yeah.
So now if we take sphere B contribution, point A is a point inside of the sphere. So we'll use the inside sphere formula, which is sigma by epsilon.
We just wanted to repeat because I don't know, the confusion is there. We are not finding potential on outside, inside, on the surface of B. We are finding only on A because of B, right?
Yeah, but related to B, A is a point inside. So we'll use that formula.
Yeah, yeah.
So we'll get minus sigma by epsilon into small b.
Small b because the potential at any point inside B is same as its on surface.
Yes, sir.
Now, if I draw another sphere, C, that point is still inside C only, right?
Yes, sir.
Yeah.
So we'll use the formula sigma by epsilon and C.
Can you check others if you're clear or not?
Yes, that's fine.
Yeah, we are going for B. Okay. So I'll draw another separate sphere once more. Like, so this is sphere A. The point is not on sphere A. Now the point is on sphere B, right?
Yes, sir.
So this is the contribution of what on where, like, can you confirm?
So it will be contribution of A on B.
Yeah, point B because of sphere A. Is the
And
point inside, outside on the sphere, like?
outside.
So which formula?
So we'll use the first one. Sigma by epsilon. We'll take A square by B.
Sigma by epsilon. The sphere which is contributing is A. So A square by the
B.
distance is B. Now contribution of A is over. Now we are counting the contribution of
B.
B. For B, the point is on its own surface, right?
Yes, sir.
Okay. What's on the surface formula?
Minus sigma epsilon by epsilon into B.
Now you take the contribution at that B itself due to the third sphere. For the third sphere also, this point is what?
Inside.
Inside. So
for the third, I'm sorry to disturb. For the third sphere, the point B will be inside.
yeah,
right?
yes.
And point A will be outside.
For sphere A,
Now the contribution of the third sphere on point B will be what, sir? Inside or outside?
check the point is inside or outside the third sphere.
It is inside.
Yeah.
So it's inside. And the contribution of the first sphere on B will be outside.
Because it's outside the sphere B, sphere A, another point.
Okay. Okay, so yeah, I got it.
I don't know anyone have a question. We are waiting for that. Pallavi, it's fine now.
Yes, sir.
Okay. Now, can you try the third one then?
Yes, sir. So VCC.
1 minute. This is the inner sphere. Okay.
Sorry.
This is the inner sphere.
Yes, sir.
A plus sigma, and your point is where?
On C outside.
So this is your point. So I want potential on C. So this point contribution because of A will be inside, outside, or on the sphere.
Outside the sphere.
Outside the sphere, what you do?
Sigma C square. Sorry, A square,
no.
A square.
Because
by
A
C.
is a sphere contributing, right?
Yes, sir. Yes, sir.
And by the distance.
Yes, C.
Now we want the contribution at C itself due to
B.
B. Still the point is
Outside.
outside. Yeah. So what will be the contribution of that sphere?
Minus sigma B squared by C.
Yeah, I think you got it now. B square by C. For the third one, you don't want me to draw, right?
No, so for the third one, it'll be on the sphere.
Yeah.
So it'll be sigma C by epsilon.
If you all can check, this is the expression for the formula. We can take some common factors and out, get the final. No, I can't take outside, right? I could have taken if I have a c square in the denominator. It's fine, no need. It's a very easy way, simplest way to solve the question, but it needs some concept which sphere you take, which point you take, like that. I don't know, you listened to me when I started the topic. I told 4 or 5 times because I know it happens every year. Everyone will be very casual. Okay, okay, I know, I got the concept. When you try to apply, the confusion will come. Which R you take on the top, which R you take down, like. If you're fine with this, I'll complete the question and go back to the other method if you want.
So what is the other? Is there any other method to solve this?
Another method is a longer method. We use equal to KQ by R formula, right?
Okay. Yeah. Okay.
But this question, can I complete? This is okay with you till now?
Yes, it's fine.
This is the second part for the question. We complete, and if you want to go, second method will go. Anyone have a question now based on this? They told potential of A is equal to potential of C. You can substitute and get the result from it. Sigma by epsilon anyway get cancelled.
Is it C is equal to A plus B?
Yeah. Is this fine with you?
Yes, sir.
Do you want to see the other method, or if this is convincing, then I don't want to trouble you.
This is fine, sir.
Anyone would like to see the other one?
This is fine.
So what point you have to be careful in this?
So with the outside formula.
You should be clear which point. Is it inside the sphere, on the surface, or outside for the other three spheres? Can I clear this, or any more questions on this? Can you check this question? It's partially similar to that. For convenience, here I'm marking the points as A and B. What you find?
Potential difference between one point on the big one and one point on the small sphere.
So I marked it as A and B. So you need to find the potential of A first, then B.
What question number is this?
Question number, the previous one, I think. 34, page 53, 34.
Okay, sir. Thank you.
The last part is not there, okay? Name the device which work on this pack. That is out of syllabus now.
Is it compulsory to find A first?
Joanna, I didn't hear it.
Is it compulsory to find point A, like potential at A first?
No, first you can find anything. No compulsion.
Like, are we assuming it's going from A to B? I mean,
No, I just want 1 point first, second point next. There's no problem in that. Any point. Okay.
okay.
So if you want me to take B first?
No, so I just asked. So,
No, it won't make a difference. We have to find which is higher or lower, right?
yes, sir. It's okay.
So A will have how many contributions?
2.
2.
Yeah. Sonika, can you continue?
Yes, sir. So the first one will be on the sphere A,
Yeah.
and the second one will be on the sphere, like what is happening, like influenced by B on A.
Yeah. Can you continue? Correct. Yeah.
So the first one will be sigma R by epsilon plus sigma
Which are?
small r,
Yeah. Okay.
and then for the sigma big R by epsilon capital R.
Yeah.
So
But
that
correct.
Yes.
I didn't hear you so many times. Now only I heard your sound. So only continue. Okay. Is it clear than the last question we discussed?
yes, sir.
Okay. Fine. But there's a problem with this. They didn't give sigma in this. They only given Q.
Yes, so we use the KQ by R formula.
Yeah. Or you can change sigma here if you want. You know sigma, right? Fine. No, the other way, right? They didn't give same sigma here. So we can't use sigma.
So this will be a longer method. So then it will be better if you use the other formula.
Yeah, it's better to use the other one. This will take time. Can I remove this? It's fine. Not wrong what you said. Correct. Okay. So the other formula was K Q by R for outside and KQ by R for inside and on the surface. Can you tell me A due to A? K.
So that would be K small q by small r.
Yeah. Plus.
K big Q by big R.
Yeah, that's it. Both are like one is on the surface, one is inside. What about B? For point B is outside A or inside or on the surface?
Inside.
Point B.
Or so you're talking about the potential due to B?
Potential on B due to A.
So it'll be outside.
Yeah, so which formula you use?
KQ by R.
Yeah, which Q, which R?
It will be big Q by
No, who is producing the potential?
small r. I mean small A.
Yeah, so it's charge, right?
Yes.
Then,
And then
which
it'll
R?
be capital R, right?
Yeah, because you're finding from the influence of this one here, right? The distance is capital R.
Yes, sir.
Yeah. Plus.
So it'll be K capital Q by capital.
Yeah. Can you all confirm this is fine or no? Anyway, you didn't ask me the second method. The second method came here because this is easy here. Second method, no sigma is given. Are these potentials fine on A and B?
Yes, sir.
Then find which is greater in that. Charge always flow from,
A is greater.
charge always flow from
Higher potential to lower potential.
So this is KQ by R, common in this, both. KQ is common. Only difference is small r and big R. And we know small r is less compared to big R. If small r is less, that potential should be greater. Fine. Check. If R is greater, that potential should be less. It will be B or A.
A has more charge.
A has more.
Potential, sorry.
So charge flows from
A to B.
charge flows from higher potential to lower potential.
So if we're finding the potential difference between 2 points, then it'll be VA minus VB, just because it's higher, even though it's not mentioned in the question.
So that gets subtracted. KQ will come common out. Delta V is VA minus VB. So KQ by R get cancel capital. And KQ comes common out. 1 by R minus 1 by R. If you want to take LCM, you can take that. That's it. I'm waiting for any more questions on this or the previous one. So we'll leave the sphere part with that. These are two most common questions asked from sphere related to potential. So if you respond to me quickly, yes or no, I don't mind both. We can move to the next and do more questions.
Yes, that's fine.
Anyone else want to wait? Mayuka?
No, sir, I got it.
I think this whole question we have done, right? 27 to 31, right? I think we have done 28, we have done 27, 29, 30.
Yes, sir, it is.
I just clear it up, which all topics I missed or left in between. And there are a few questions based on those concepts. One, we have a relation connecting the electric field intensity and potential. Okay, fine. We learned E differently, V differently. Now there's a connection between the two. We're trying to establish the connection between E and V. Say plus Q charge. This is just representing the distance from the charge. We take a point random here. The distance from O to that point is R. Imagine a charge is moving randomly in any direction. So this charge experience is a plus Q test charge like we have taken before. This experience a repulsion from the source charge. Which direction?
So like towards the right.
Yeah, it is at this point. So plus Q plus small q repel. This is the direction of the force. This is the electric force. That's equal to, we wrote last time as K Q by R square. Here we want relation between E and V. So I'm just trying to change this term as E. You already learned this. And this is same as QE. At that point. Now, to overcome the effect of the source charge, the external agency has to do or apply same force but in the opposite direction. So this is the external force. So this will be the angle between the displacement and the force theta. This is the direction of the external force to counter the electrostatic force. So F external equal to minus of F electric equal to minus Q E R. This is all we have done in the last topic for the potential, but all I'm changing KQ by R square as E because our aim is to get that. Now find the work done for a small displacement. F external dr, because displacement is dr, then cos theta. You can substitute F external as minus QE R dr cos theta as dw. Any questions?
So why do we take an angle? Like shouldn't it just be like a straight line?
Yeah, normally we do, but it can be possible the charge can move any direction, right? With taking a general case and finally we can do the other cases, special case, theta becoming 0, 180, 90 and all.
So okay, but then how does it move in like this direction? The force is pushing in like
No,
right direction.
it is
How
not
does it?
because of the charge. It was moving in that direction initially.
Oh, okay.
Then you have to counter the effect of what? Electric.
The potential. Okay, so got it.
it's already coming in that particular way into the field. Once it enter the field, our responsibility to what cancel the effect of the electric force.
Yes, understood.
We have done first case straight line. That time exactly we got theta as what? 0. Now we take a random angle so that this can be a general case for all the options, right? It can be right, left, up, down, all the angles. Okay.
Yes, sir.
So if you divide both sides by Q, we got V as W by Q, VR, W infinity to R. So what will be dW by Q? Small work by charge.
dv.
Yeah, dV. So I can change this dW by Q as dV equal to minus ER dr cos theta. So if you rearrange this, you'll get minus dV by dr equal to E cos theta. This is a general relation. This is a relation between electric field intensity and potential in differential form. If theta is 0, cos 0 becomes 1, you get a special case relation. That was she was asking, E equal to minus dV by dr. This is also commonly used. If you can check and clarify, this is okay with you. It's a derivation type small 2 mark which can come maximum. Obtain the relation between electric field intensity and electric potential. If you write the second relation in words, E is the negative gradient of potential. Electric field intensity is the negative gradient of potential. Gradient means always you take the change of the quantity with the distance. If you are not fine, tell me, I'll go on what's the meaning of gradient.
Yes, sir. Can you explain that?
Yeah. Last year we have seen something called velocity gradient. If the speed changes, like this is a layer moving with 100 meters per second, just for understanding, and this is a layer moving with 50 meters per second, and the distance between these two is 10 meters. So what is the change in velocity between the two layers?
50 meter per second.
That is for how much distance?
10. So the velocity gradient is 5.
Yeah. For 1 meter, how much? 5 meters per second per meter. So gradient of a quantity will tell you how much it changes per meter.
Okay, sir.
Or if you take a hot body and cold body connected by a system, maybe here I have 100 degrees Celsius temperature. This become 80 degrees Celsius temperature by a distance of 10 meters. What's the temperature difference?
20.
For what distance?
10 meter.
So what's the temperature gradient then?
2 centimeter by meter.
2 degrees Celsius per
Meter.
meter. Means every 1 meter you go, the temperature will decrease by 2 degrees Celsius.
Yes, sir.
I have to add 2 more points in this if you are confirming this is fine with you.
Yes, it's all right.
Now the second one is a minor deviation from this step. You integrate both sides. You write separate, okay? I can write on the side here. Integral infinity to r dv will be minus integral infinity to r er dot dr. Because a dot b is ab cos theta. So this integral dv becomes, okay, this is not r, this is for b, okay? B initial to b final. You can't put r with dv. dv is variable, so b initial to b final. So if you take b initial to b final, this will be r initial to r final. If you take 0 to v, that will be infinity to r, because infinity potential is, I don't know, it confused you, I'm clearing it. First mistake I did, I wrote r. You can't have potential limit changing from r. Either you can have b initial to b final or 0 to b final. So this will be then infinity, because at infinity only 0 potential, infinity to r. So b at r will be equal to minus integral infinity to r e dot dr. So this is again relation between b and d. This is in integral form. This one is in differential form.
So the final VR is potential difference.
This is not potential difference. It's a difference only, but difference from 0. So it will be the potential only, that point. What's the potential at infinity?
Zero.
Yeah. If you put v initial and v final, this will be r initial and r final, then it will be potential difference. Okay.
So I wanted my R to, okay.
Now, when we do the potential, the definition is from what? Infinity to r, right?
Yes, sir.
I can add here. P is the negative line integral of E electric potential is the negative line integral of E from infinity to that point. electric potential at a point is the negative line integral of electric field intensity from infinity to that point. Close here. Is that fine with you?
Yes, sir.
Can you hear me clearly?
Yes, sir. So could you please explain the points about the limits, like from 0 to...
Yeah. Can I clear then the other part? Only just I take this point.
Yes, sir.
We have a relation dV equal to minus E R dr cos theta. Fine.
Yes, sir.
I'm moving from infinity to R. Okay.
Yes, sir.
So what is the potential of infinity? We are starting from infinity to move a charge when you find the potential, right?
Yes, sir.
That is by assuming infinity potential to be zero, right? No work is done.
Oh, yes, sir.
If a charge is at infinity, the charge is not under the influence of any other source charges.
Yes, sir.
The potential is zero at infinity.
Yes, sir.
When you come to R, there will be a potential finite, right?
Yes, sir.
So if I integrate dV, the limit should be what?
0 and the final potential.
Yeah. Or I can have R1 and R2, R initial and R final. I'll take up that after this, okay?
Okay, sir.
Is that fine?
Yes, sir. It's fine.
Now, if I go to another point, that's what I wrote here. This will come as what? B, okay?
Yes, sir.
Now it's between 2 points. What will happen?
So we'll take the limits as B final and B initial,
Yeah.
and it'll change in V, delta V.
This will be R initial to R final. That time this will be V final minus V initial.
Yes, sir.
I need to add just one more point in this last. If the field is uniform, uniform electric field, V final minus V initially equal to minus integral R initial R final ER dr cos theta. For a uniform field, the E and theta remains the same, right? The angle remains the same. Can you confirm?
Yes, sir.
This will go as minus E cos theta. What will be integral dr?
R.
Yeah. It will be in the limit R final, R initial to R final. If I replace this as a distance, it will come as I've taken R final minus R initial as D.
So there's no need to write ER then, right? You can
Yeah, you
directly
can write ER, it's not a problem, right? Uniform field means you don't want to write ER, right?
Yes, sir. Okay.
Everywhere E will be the same, right?
Yes, sir.
Yeah, one change with that. This last result you need to learn because it's used for numerical questions. Even these two results where I wrote word meaning. I wrote one word meaning here. Electric potential is the negative line integral of electric field. Or even I wrote here, electric field is a negative gradient of potential. Why? Because they can ask you, they asked before, name the quantity which is a negative gradient of potential. Is it a scalar, vector? Arrive at an expression for like that. They will not tell you directly, it's E. Same way they can ask you here also. Name the quantity which is the line integral of electric field. So it should be clear what quantity is line integral of electric field, what's the gradient of potential. Okay.
So could you show the uniform field, the last part? Thank you, sir.
check any questions you have on these topics. And every question, every topic may not be like that interesting or like, I think the sphere question everyone was live basically because it was little different. Is it okay?
Yes. Yes.
Did we make a note the work done is independent of the path? We already know, right? Electric field is a conservative field. Work done does not depend upon the path.
Yes, sir.
Okay. If not, you have to make a note. The work done in moving a charge in an electric field is independent of the path. It depends only on the final and initial positions. Means if you start from point A and you reach point B, we have seen this last year also for conservative field. This is one path. This is another path. This may be a totally different path. Right? So this is work 1. This is work 2. This is work 3. So which one is more, which one is less in that?
It's all same, sir.
All the case work done since the initial point and final point are same. Work done will be the same. I to add one more note if this is fine. I think it's fine, right? It's already you know the concept. We just wrote it once more to remind it. Okay.
Yes, sir.
One more point we need to learn related to the previous connection only. Okay. If you have a charge, maybe this is a positive charge. So what's the direction of electric field?
Positive to negative.
Yeah, I didn't give any negative. So what you should do then? This one negative, you can just say what radially outward, right? For a positive charge.
Yes, sir.
Okay. In this, I'm taking 2 points. This is point B. This is point A. The distance for B this is our final or RB, fine, R to B. And this distance is RA. So which has higher potential, A or B?
B.
Yeah, because VB is what? KQ by
Closer.
RB. VA is KQ by RA. So since RB is less than RA, you can say VB is greater than B. Fine, that's the meaning, right?
Yes, sir.
So can you check the direction of electric field from A to B or B to E? Fine.
Yes, sir.
Is it from higher potential to lower potential or lower potential to higher potential?
Higher, but no.
Higher to-
Higher, but no.
Yeah. What about a negative charge? If you take, it's a negative charge, Q exactly same. So this is the line. So this is the direction of field. We are taking again the point same. This is point B. This is point A. This distance is RB. This distance is RA. So potential of B, potential of A, which is higher potential?
B.
A, because even RB is less than RA, but
Oh, yes, sir.
are you changing the answer?
Yes, sir. The A, right? Because you have to push it away from the.
No, I want a final confirmation. Which potential is higher, you're telling?
Yes, sir. A.
Yeah, that only told me first also, right?
Yes, I said B first.
Told me B first.
Yeah.
Okay. When you write VB, it will be what? Minus KQ by R, right? Potential, you have to count the negative of the charge as negative only, okay? Yes.
Yes, sir.
For sample value, not correct. If I'm taking this as 100 and this as 80, what will be the answer here? So which one is greater in this?
Minus 80.
Yeah. So same. What? VA is greater than P. So see the direction of the field from higher to lower or lower to higher.
Higher to lower.
Yeah. So that's a common concept. The direction of electric field is always direction of decreasing potential. Even you had a relation E equal to minus dV by dr. This negative sign means like this. dV is a potential difference. This is negative of that, opposite of that. Electric field is always directed in the direction of decreasing potential. If you're fine, then we can go to a few questions based on these concepts we discussed.
Yes, sir.
So this is a concept, it will help you again solving the questions, okay? That's understood, I think, from this discussion, right?
Yes, sir.
This one have more questions from the previous chapter also, okay? I searched, maybe it is there in the material, but I didn't find out, so I'm making a question for that concept. You waiting for me to start, or you started already?
So started.
So to find the work done. A to B.
The potential into charge.
Potential difference into charge. Because there are 2 points, right? Infinity only potential will come. Okay.
Yes, sir.
So here C is of no use, right? The point C.
That's what I want to add one point. We made a note, right? It's independent of the path.
Okay, sir. Yeah.
Just given for confusing you. That's okay. This is the general formula for work done. The charge which is moving, final potential minus initial potential. The one stationary will be the source charge. That is the one producing potential at A and B. The moving one will be the test charge or the small charge Q always. So what is VA? K Q by RA. VB. K Q by RB. This is RB and this is R. So you should be doing final, right? Final potential. Final VB's RB is 25 centimeters. Actually, you should have taken it out without writing, substituting less work.
So for VA, why are we taking capital Q?
Who is producing potential at A and B? It's not the moving charge, right?
Yes, sir. Okay.
Remember when we did the potential derivation, one source charge was stationary. We moved a test charge and final expression was in terms of the source charge, right?
Yes, sir. Okay.
So that is a note again. The charge which remains stationary will be the, wherever 2 charges are given, no confusion. The stationary one will be the source charge and the moving one from one point to another point will be the test charge. And the potential is all due to the source charge. Oh, 11 minus 3, 8. And this to minus 2 common out. Minus 6. 9 into 10 to the power of 9 plus 2, 11 minus 3, 8. Minus 2. 1 by 25 minus 1 by 10. You could have taken 5 out again. Five is out. This will be 5. This will be 2. 9 into 10 to the power of 8 plus 2, 10. 10 minus 6 is 4 by 5. 5 is again 10 by 2. 2 minus 5 by 10. So 9 into 2, 18. Into 10 to the power of 1, 2. 2 tens will go 2. 2 minus 5 is minus 3. 54 minus into 10 raised to 2. 5.4 into 10 raised to 3. Work done, joules.
So when we're solving the sum, do we have to write like work done is dependent of path, or we can just like do the sum?
You can do, but it's always better to add a line since the work done is independent. The via point is not important. Okay.
Okay. Okay, sir.
Even you do also that indirectly taken into account. Okay.
Yes, sir.
So I don't know, later confusion should not come. If you are not clear, make a note of this, how to understand when the charges are given. Which one is the source charge, which one is the test charge. And potential is always due to the source charge. So you can tell me it's fine.
Yes, sir, it's fine.
Checking the 15th question. This is point A, this is point B, C, 501310. It's moved from A to B, then to C. Calculate the potential difference between A and C. It's a uniform electric field E. So you know the formula for potential difference, right? Just now only we did. I told it box the last equation we learned. Fine.
Yes, sir.
Yeah. So E is not given. We just use E only. What's the distance from the initial point to the final point? A and C. This is A initial point. This is C final point.
So 4 units.
It is 1 and 5, right? 4, yeah. Cos theta.
So 1.
Sorry.
Says it 1.
Yeah, because the charge is going from A to C. This is the force and the displacement same, right?
Okay, so theta will be 180.
Yeah. The displacement is towards left. The field is towards right.
Yes, this will be -1.
Minus will go right.
Yes, sir.
Take the angle between these two quantities, be -1. Electric field is right, displacement is left. It's fine.
Yes, sir.
Now, what about A and B? You're moving from B to C perpendicular to electric field, right? So delta V of AC, I can split as what? Delta V of AB plus delta V of BC, fine. Difference from A to B, then B to C. The work is done part by part, A to B, then B to C, the total work.
Yes, sir.
But we know B to C, what's the angle?
90.
90. So this will be 0, right? So delta V AC will be same as
Shall be same as delta AB, VA.
yeah. The third one is delta V between B and C. I'll just finish it. 1 minute, we'll be done. Okay. Which is more potential, C or A? Just now only we learned one concept. Electric field is in the direction of
Lower potential.
yeah. So it moves from higher to lower potential, right? So which point is higher potential, C or A? Can you confirm?
So A is great.
C is at higher or lower potential compared to A? Electric field is from, this is a concept. So electric field is directed from higher to lower potential. That means VC is greater than VA. Fine.
So how do we know C is greater?
Sorry.
How do we know C is greater?
What's the direction of electric field? Can you see this?
Yes, sir.
So this is going from C to A, right? No.
It's from A to C. Right?
No. The electric field lines, not the charge.
Yeah, yes, yes. C to.
Yeah. Electric field is not the work done or the charge. Okay. Electric field is always from higher to lower potential. Work you can do anyway. Okay.
Yes, sir. Okay.
So because of this, C is higher potential. The last point, work done to move a charge from B to C. We already know this potential differences. The force and displacement are perpendicular otherwise. So the work done will be 0. Once you confirm this, I'll mark a few more questions same type and we'll stop it.
Yes, so it's fine.
You can mark 16, 17, 18. $20, till 22. That questions 16 to 22. And now you have exams. Those who don't have exams, try. For those who finish the exams, after that you get time to try. Okay. That's only these questions. Only 5, 6 questions. Okay. Thank you.
Thank you, sir.
Yeah.
Thank you.
So till Ramadan is over, we'll have class at 7:15.
Yeah, 7:15.
Okay, sir.
Thank you, sir.
Thank you, sir.
Yeah.